Hello, everyone. We are starting one more lecture from our Distinguished Talks initiative. Hello, everyone. We are starting one more lecture from our Distinguished Talk initiative. Today, we have the pleasure to be joined by Dr. Mario Lanza, who is currently a full professor at Soochow University in China. Dr. Lanza is an extremely active member in our field, being in the advisory board and technical committees of several world-class journals and conferences. And since last year, being a distinguished lecturer of the IEEE Electron Devices Society. Among the many accomplishments and impressive results in his career, I highlighted the Young Investigator Award from Microelectronic Engineer in 2017, and the Young 1000 Talent Award in 2015. We, from the ED-SSC South Brazil Joint Chapter, are delighted to have you with us today, and I'm sure that many of our members are looking forward to this talk. So, Dr. Mario Lanza, the floor is yours, and thank you very much for the presentation.
Thank you very much, Vinicius, for the presentation, and thank you to everyone who is following this presentation in Zoom and also in YouTube. So I will just switch off my camera and probably Vinicius too, and then I'm going to start to show my slides. Vinicius, you can see my slides now, right?
Yes, I can see the PowerPoint.
All right, fantastic. So before starting with the technical talk, please let me just in 3 minutes acknowledge the support from the Electron Devices Society, because this lecture is given as a distinguished lecture from the EDS, and the EDS mission covers all aspects of engineering. Our mission is to promote the contact between different members from working in different fields, so that people and our members can remarkably improve their professional career. The Electron Devices Society has a board of governors that is being very active in all regions of the world, and it is carrying out multiple activities like related to publishing, related to education, and giving technical recognitions, organizing international conferences, helping to different communities to develop. It has, when you listen a talk from the Electron Devices Society, you have this, you can be certain that you are watching premium quality. So this is something very important. I really encourage all people working in our field to enter in this exciting community, because it has given me a lot of advantages, and I think it can be very advantageous for multiple young scientists. So I really wish you can take a look to the website of EDS and maybe to become a member if you are interested. So I'm going to switch off to the technical slides now. So Vinicius, can you see my technical slides?
Yes, I can see it.
Fantastic. So here I'm going to start my talk today, which title is Nanoelectronic Characterization of Advanced Materials Using Conductive Atomic Force Microscopy. And I would like to start by thanking all the members of my group, all my students and my postdocs, because they are extremely hardworking. They have been producing a lot of data, many more data than I could handle only by myself. So I think it's really a privilege for me to work with all of them, and also to my collaborators, especially to Professor Philip Wong, Professor Chin Kong, and Professor Andrea Ferrari, who have been very active in the field of 2D materials and have been a very big inspiration for me. So everything that I'm gonna explain today can be found from our publications, and these that you see here are the main 2 publications that I would like to highlight. The first one is one review I published last year with Dr. Fei Hui in Nature Electronics, and the second one is one book that I edited a couple of years ago which title is Conductive Atomic Force Microscopy. This is the outline that I will follow, and I will start by making an introduction on how to observe resistive switching with the conductive atomic force microscope, because it is one of the main applications. So just let me briefly introduce how we use this tool. The conductive atomic force microscope is based on a conductive tip that it is placed at the end of a cantilever. And one potential difference is applied between this tip and the substrate of the sample. In this with this technique, normally we analyze ultra-thin dielectrics. This was the main use when the tool was invented in 1993 in Cambridge, and it is still one of the main applications. So here I'm going to show you one that explains how this works. In this video, you can see the tip of the conductive AFM, that it is scanning the surface of the sample. And when the potential difference is applied, you can see that the current signal can be recorded. And when there is one defect in the material, the current signal fluctuates. And then if you can scan the surface of the sample and move the tip from one line to another, you can make a three-dimensional map of the electrical conductivity of the sample that you're going to study. And at the same time, because it is based on atomic force microscopy, you can also construct one topographic map. And these two images are constructed simultaneously, but at the same time independently. One is constructed based on the deflection of the cantilever, the topography, and one is based on the signal recorded by the preamplifier connected to the tip. And that is the current signal. So this is amazing because you can study both mechanical and electrical properties at the same time. In the past, I have used this technique to study resistive switching and dielectric breakdown phenomenon in general. So first, let me show you one brief examples of what is resistive switching. Resistive switching is a property of some insulating material that when they are placed between two metallic electrodes and one potential difference is applied between them, you can change the electrical conductivity of this material. Here you can see one example. I have the two electrodes and the dielectric, and when I increase the potential difference between them, I can see that the conductive filament is being formed and destroyed depending on the polarity of this electrical field. So using this technique, I have analyzed the resistive switching in many different materials. Here you see one example. We were the first team in the world who demonstrated that the resistive switching in polycrystalline high-K dielectrics was produced only at the grain boundaries. And this was possible because the conductive AFM has a very high lateral resolution. So it's a very great advantage compared to traditional studies that use the prof station, for example. So this study was possible because we modified the conductive AFM, because the standard conductive AFMs have very strong difficulties to measure this. And the reason is that in order to measure resistive switching, you need to apply high voltages to form the filament at the beginning. You need to measure high currents. The voltage stresses that you apply need to be current limited. So you need to apply a current limitation. And also you need to measure two polarities. So this is something one conductive AFM standard cannot do. You can see here the block diagram of one standard conductive AFM. And this is the window that you can measure. You can only measure currents up to some nanoamps. You can only apply voltages up to 10 volts. And you cannot measure both polarities, because if you are measuring in air environment, you have a water meniscus between the tip and the sample. And you can induce local anodic oxidation if you inject electrons from the tip. This is a problem of chemistry, but this is very well known in our field. So we solve these problems first by performing our measurements in vacuum This solves the problem of the local anodic oxidation and allow us to measure with both polarities. And the second problem was solved by replacing the preamplifier of the AFM, which has very narrow current range, by a semiconductor parameter analyzer. And then you can perform the same test that you perform in a probe station, but on the tip of the conductive AFM. This setup was very successful and immediately adopted by other top scientists, like, for example, the first people who adopted this was in the University of Manchester. However, I have to say this has one important problem, which is this setup can only be used to apply ramp voltage stresses in one specific location. The tip cannot be moved laterally because coordinating, synchronizing the semiconductor parameter analyzer with the vacuum, with the movement of the tip is really complex. So in order to solve this problem, what we did back in 2008 was to fabricate one logarithmic preamplifier that it can convert the signals very fast, much faster than the SPA. And for this reason, this can be used to during the lateral movement of the tip. Thanks to this setup, we created the first current maps with multiple orders of magnitude in the current scale, as you can see here. And our setup was later commercialized by companies like Agilent Technologies, and right now is being commercialized by Park and by other companies. So here, using the conductive AFM, I have shown you here that you can see, detect where are defects in the dielectric. I'm going to show you also how to make three-dimensional studies, how to analyze what is below the dielectric. And this is something that can be done in different ways. I analyze the pros and cons. This is the first way. For example, imagine that you have a real electronic device that is based on a top electrode, an oxide, and a bottom electrode. And you apply some electrical stresses at the probe station. And after that, you want to analyze the sample. You want to see where are these defects formed and where are the conductive filaments formed. So basically, one option that you have is to etch the top electrode with one chemical method and then use the tip of the conductive AFM to scan the surface of the sample. If you do this, you can obtain something as you can see here in these A and B panels. You can see one capacitor that has been set to high resistive state shows some few conductive spots. That shows similar current, but one that has been set at low resistive state show first much higher currents, and second, if we change the scale, we see one of these conductive spots that is dominant. So this is very interesting because the AFM can allow us to prove that the low resistive state has no area dependence, which is something that was previously observed at the probe station level. But here we demonstrated in situ and we observed the properties of the single filament that dominates most of the current. This can be also used, this method can be also used to analyze, for example, degradation of field effect transistors. Here in this work, we perform a similar study in which we stress one field effect transistor with NBTI and with channel hot carriers, and after that we etch the top gate and we scan the surface of the channel of the dielectric on the channel with the conductive AFM, and we could find some interesting differences. However, this technique has one problem, which is that that the etching could damage the surface of the oxide because the selectivity of the method maybe is not perfect, and you can damage a little bit the surface of this oxide. So one method that can be employed is the use of the tip of the AFM to etch this electrode. And then if you do that, you can etch all the volume of the top electrode, and after that you can see the size of the conductive filaments across the dielectric in both states, for example, in high resistive state and in low resistive state, and you successfully can see what is below this electrode. This can be done. The tip can be used to etch the top electrode of the device. However, in 2014, some people noticed that, well, the tip could be also used to etch what is the bulk of the dielectric and observe some how the size of these filaments evolves with the depth inside this dielectric. So this was done in the past, and people could make three-dimensional current maps of these dielectrics. So for example, in this work, one of my colleagues in IMEC, he performed this three-dimensional characterization of one single conductive filament by applying one electrical stress and then mechanical stress to etch, and then electrical stress to read, and then mechanical stress to etch. And like this, he made 7 slices, and he rendered them three-dimensionally, and he could make this beautiful study. Very, very useful study. However, I have to say that this etching using the tip of the AFM, depending on the materials that you use, it could bring some associated problems. For example, we have observed that in some materials, the surface of the sample where you etch can change the properties. Here you can see the example of one sample in the top row. This is one sample that is just silicon. And then when we etch and we apply an electrical stress everywhere, we see that the regions where we have etched are more insulating, which means that even if it's silicon, we have changed something. We have changed the electrical conductivity at the etched region. This can be also seen in the TEM images, actually. If we do cross-sectional analysis of the etched region, for example, here, you can see very clearly, we have aluminum oxide where we etch and we cut with the TEM everywhere, and you can see the etched region. And if we zoom in this region outside and inside, we can see very clearly that there are changes. There are some black particles that, if we focus on them, we observe they are a phase change. The material that was amorphous has polycrystallized, probably due to the high temperatures produced during the etching by the frictions of the tip with the sample. And this, we have demonstrated this with some simulations that some materials like silicon can become amorphous when we etch it, and the opposite, some amorphous oxide can become polycrystalline due to the temperature. So in order to avoid this problem, when I was working at Stanford University, together with Professor Paul McIntyre, we developed one interesting method to apply electrical stresses using into dielectrics using ionic liquids. Instead of one solid metallic electrode, we use an ionic liquid conductive electrode, which is what you can see in this schematic. So basically, the structure looks like this. We use a very thick photoresist with some top electrodes on top, and we put one drop of the ionic liquid that contacts both the dielectric window and the top electrode, and we apply some electrical stress with the top probe at the probe station and the bottom probe. Here we can stress the dielectric, and after that, the beautiful thing of this method is that we can rinse the ionic liquid, and after that we scan the bare surface of this dielectric with any technique we want. Here you can see some SEM images of the samples before the stress and after stress, but actually we can apply any other technique that we want. The fabrication of this structure is not difficult. We have published this in the proceedings of IPFA conference in 2018. Basically requires a couple of photolithographies, but it's not difficult. We can really help you to do it if you are interested on this method. And here you can see some examples of what this method allowed us to do. We did 2 experiments. In the first one, we use one ionic liquid that is not very conductive, and we can observe clearly that before the bias, the conductivity of this material is low. After the bias, it increases. And when we apply negative bias, it decreases again. So this is demonstrated that you can set and reset the conductivity of this dielectric. And by doing tests in different areas, we observe that both the high resistive state and the low resistive state in this stress are both dependent on the area, which make us think that this is a distributed effect. But because we are applying the test with the prof station, we cannot be sure about this. So the way that we have to confirm this is by doing electrical maps. These electrical maps were done by one of my students in the fresh samples after the first set, after the first reset, and after the second set. And you can clearly see that the density of spots increases and decreases, confirming that first, there is resistive switching, and second, this is a distributed effect. Actually, we made some statistical analysis of this area and the maximum current driven by the spots, and it can be clearly seen that the maximum current increases for the set, decreases for the reset, and this is proved statistically because we don't have information about one point or one curve. We have information about multiple conductive filaments that we have, or maybe leaky spots that we have analyzed with the tip of the conductive AFM. Actually, this method also allows us to apply chemical tests. So here you can see one very interesting oxygen detection with nanosims, in which, depending on the time that we apply this electrical stress, we can see that when the time increases, the density of oxygen at the surface also increases, which means that this increase of the conductivity is related to the formation of oxygen vacancies inside the dielectric. This was published in Nanoletters in 2017. You can see more information in that paper. In the second experiment, we use an ionic liquid that is more conductive. And this allows us to increase the conductivity of the sample much more. What we can see here is that dependently on the area of the window that we have patterned, the increases, and in both cases, the conductivity is similar after the set, which is indicating that this is not an area distributed effect. If it is not an area distributed effect, then all the current should be dominated by one single conductive filament or one single conductive spot. So in the next experiment, together with my student, we did one experiment that it was really, really, really difficult because we needed to find one conductive filament that is around 4 nanometers in one window, which diameter was around 40 micrometers. So this was a very challenging experiment. We need to increase a lot the resolution of the map, which decreased the speed of the scan. And this scan that you see here took us nearly 2 hours. But at the end, we finally found successfully that all the points that you see here, according to this scale of 150 picoamps, they don't show remarkable currents except one single point, which is driving most of the current across this structure, across this dielectric in low resistance state. So in the next step, I wanted to also show you one advanced setup that we have used recently to test the electrical properties of nanomaterials. This setup is based on the combination of the CAFM with other techniques. So the first one is the formation of local defects in this dielectric using in situ TM. Here you can see one map in which one TM image in which the authors of these papers, they take one TM image for different times as the stress proceeds. And you can see how the filament is forming slowly, and when the bias is when the bias is removed, this filament is self-disrupted. This can be also used this technique is beautiful because it allows you to correlate the electrical changes with the morphological changes in the dielectric, and at the same time, if you have EDX or EELS in this TEM machine, you can also detect the chemical rearrangements that have produced this electrical stress, which is wonderful because it allows you to observe in situ the switching mechanism in this material. And the second example that I wanted to highlight is the introduction of one conductive AFM inside the chamber of a scanning electron microscope. Here you can see the SEM image of the tip contacting one sample that consists on zinc oxide nanowires. And in panels C and D, you can observe the pictures taken by the SEM and by the AFM of the same nanowires. So this is something interesting because, again, we could correlate the electrical signals with the image obtained by the SEM. And this is like if you were observing this current fluctuations in situ, and you can correlate it with the mechanical properties. So in this slide, I would like to show you one video of what you observe in the SEM when the tip is scanning the surface of the sample. You can clearly see how the tip is contacting the nanowires, and actually you can also put the tip on the nanowire that you want, and you can bend it intentionally by moving the tip of the conductive AFM. So actually, this allows us to correlate the mechanical bending of the nanowire with the electrical signals collected by the tip of the conductive AFM. And this is very useful. And in this paper, we solved one problem that was unresolved for 13 years. In 2006, Professor Chonlin Wan from Georgia Tech published in Science one revolutionary paper where he demonstrated that zinc oxide nanowires can produce current by piezoelectric effect. And they did one experiment with one standard conductive AFM that scans the surface of the sample. So until we did this work, it was thought that all the current produced is related to piezoelectricity. But thanks to this setup, we could demonstrate that the currents produced are not only related to piezoelectricity, but also to contact potential difference and to triboelectric effect. Because we see one peak of current when the tip touches the nanowire, even if it's not bending it, and another peak of current when the tip starts to slide on the nanowire, even if it's not bending it. So if the tip is not being bent, the current cannot be related to piezoelectric effect. It should be related to these two phenomena that I have just described. So that's the beauty of this setup. We could demonstrate this because we were seeing the bending of the nanowire in situ during the scan. Thanks to the SEM, of course. Okay, in the next step, I wanted to share with you some other studies that we have done on two-dimensional materials characterization. So I started to work on graphene in 2010. That's the first 2D material that I analyzed, and I started to study it using most of the techniques that were studied in that time, which is scanning electron microscopy, atomic force microscopy, scanning tunneling microscopy, also SEM and OJ electron spectroscopy. And we found something interesting. We were able to quantify the amount of wrinkles. We developed a method to reduce the amount of wrinkles by increasing the roughness of the substrate. And we also studied the passivation properties of graphene, the anti-corrosion and anti-oxidation properties of graphene when coating different types of metals. But then I started to decide to apply the conductive AFM to analyze some properties of 2D materials. And as I mentioned before, the conductive AFM is unique because it allows to measure at the same time mechanical and electrical properties at the nanoscale. So in 2014, I saw a paper in Nature in which it was demonstrated that molybdenum disulfide is a piezoelectric material. And it was demonstrated at the device level by bending this material. This material can be easily bent. As you can see in this video, this is a flexible material. If you put it on a substrate with holes, you can bend it. So our question was how could we measure this at the nanoscale? And we decided to fabricate this material by liquid phase exfoliation. We fabricated one piezoelectric ink on molybdenum disulfide, and we deposited on a substrate that was patterned with some holes, so that we could go with the tip of the AFM onto the suspended molybdenum disulfide and push with the tip, and at the same time measure the electrical current that was being produced. And we observed very clearly that the amount of current generated increased with the contact force that we applied, demonstrating that this material is piezoelectric and that the current generated is related to the strain of this material. And in the next step, I also decided to study some 2D materials-based field effect transistors, like, for example, graphene-based field effect transistors. And recently we used molybdenum disulfide to fabricate one photo transistor that has a very high light-dark ratio and a very low power consumption. That is why Nano Energy accepted this material for publication. However, I have to say that in this field, there is a very wide community working and a lot of people growing graphene and molybdenum disulfide and also other TMD materials. So I decided to try to use the material for other applications. And I thought on how graphene or how 2D materials could solve some of the problems that I had in my daily life when using the conductive AFM. And this is one of the main problems that I had. The most important problem in conductive AFM science is that we use metal-coated silicon tips that are very sharp. And after you do some measurements, due to the mechanical frictions or due to the high currents, which increase the local temperature, you can damage this metallic varnish. Then your tip is not conductive anymore, and you need to use a new one. These tips can degrade really fast, depending on the measurement that you do, and they are expensive. So you always want to preserve the tip for two reasons. First, to reduce the cost of your research, and second, to ensure the reliability of the data that you are collecting. Because if the tip has degraded between the first and the last measurement, then all you have in between cannot be considered. So we evaluate what is the degradation speed of one standard AFM, conductive AFM tip. We develop one method based on an initial check of the conductivity, a sequence of current maps at a constant force and voltage, and another check of the conductivity of the tip. And we observe that for one specific tip, one specific sample, and one specific measuring conditions, our tip degrades in 13 scans. It was very obvious because initially the scans show a lot of current, which here is indicated with yellow color. And after just 13 scans, the image turns blue, which means we are not measuring enough current. So my idea was to take the AFM tip and coat it with a flake of graphene because it is mechanically stable and highly conductive. And I checked the literature in that time, and there were some approaches that were being used. The first one was to blow the material directly on a metal-coated tip. However, this involved temperatures of up to 1000 degrees, which means that the metallic varnish is going to melt, and didn't give very good results. The second one consisted on making a kind of mold and then inject 1 mold of copper covered with graphene, and then inject some photoresist in order to make the tip, and at the end etch the mold. However, these produce tips that are not very sharp. And the last method was the transfer. It was not really used on tips. It was used on kind of pyramidal samples. So we were the first group on trying this on real tips. Basically, first we fix the tip onto a silicon substrate, and then we prepare a flake of graphene, a sheet of graphene covered with PMMA, and we transfer it on this tip that was fixed. Here you can see all the stages of this process. And you can see clearly that the cantilever bends when we transfer the PMMA graphene, but after we remove the PMMA, we see that the cantilever recovers the initial position. And we see here some faults which may be related to the presence of graphene. Of course, you don't see the graphene in this SEM, in this optical microscope picture. We took some SEM images, and we also were not able to observe the presence of graphene. However, we did observe that the degradation of the tips on which we coated the graphene was much slower. We could make many more electrical measurements, and after them, we observed that the shape of the tip was preserved. We scanned different samples, we did IV curves, we did current maps, and we also always observed that the graphene-coated tips live much longer. We analyzed these scans that you see in the previous slide. This slide are for copper substrates, and these ones are for high-K dielectrics. You can see that here the current map that is collected with the graphene-coated tip looks with much better resolution, and that the currents measured are higher. And the size of the spots is smaller, which means also better definition of these defects that are being contained in the dielectric. So after that, I did that work when I was a postdoc at Peking University. We published our work in Advanced Materials. And when I started my group in 2013 in Soochow University, I thought how to improve this, because when I tried to contact the companies and tell them to commercialize this type of tips, they always tell me that the transfer was too expensive. They could not apply this in an industry. So I tried to find an easier method. And I started to work with my student, Fei Hui, and she found a very nice method, which is use liquid phase exfoliation. Basically, you just have a glass of water containing graphene exfoliated by liquid phase exfoliation. You immerse your tip, you take it out, and what you observe is what you have in the image in the right. You can really see that the graphene is coating the shape of this tip. We analyzed that the change on the resonance frequency of these tips, and we observed that the graphene doesn't change the mechanical properties of the tips. Of course, because it has negligible mass, and this doesn't alter the mass of the cantilever, and therefore it doesn't alter the mechanical properties like the spring constant or the resonance frequency. So we compare the standard tips with the graphene-coated tips, and you can see that for the graphene-coated tips, we achieve a much longer lifetime. And with the same type of tip, just putting graphene on top with this very easy method, we can scan 92 times with the same condition. And the decrease on the conductivity is much, much lower. So basically, this is demonstrating that there is a much larger lifetime. Of course, if you analyze the SEM, the tip coated with graphene using SEM after 92 scans, you are going to see that there are some particles attached, but this is something normal in all AFM tips that are used for 92 scans. The important thing is that the conductivity is maintained. We also did these experiments for many more times. We evaluate the amount of area that can be scanned without conductivity decrease with standard tips and with graphene-coated tips. And while there is a normal deviation from tip to tip, we observe that all the graphene-coated tips show lifetimes much higher than the standard tips. In this slide, in panel B, I also performed a different experiment which consisted on applying constant voltage stress and monitor the current over the time for 3 types of tips: the standard metal-coated silicon tip, the standard metal-coated silicon tip with graphene on top, and one diamond tip, which is much, much more expensive. And what you can see here is that if we compare the standard tip with the graphene-coated standard tip, the blue and the red lines, you can see that the tip that has graphene shows much longer lifetime. Here, the current densities are so high that they can melt the metallic varnish of the standard tip in just 30 seconds. And for the diamond tip, we see very long lifetime. However, the diamond coating is very rough, and this produces some contact instabilities over the time, which is something that we don't have this problem with the metal-coated tips with graphene on top, because these tips are very sharp and the metallic coating is very smooth, as you have seen before in the SEM image. We also found, unexpectedly, another very interesting property, which is when we perform statistical analysis of the many IV curves with both types of tips, with and without graphene, we observe here in panels E and D that the onset voltage of the graphene-coated tips is always lower, a little bit lower, and that the deviation is also lower. And the reason is, as we found later, thanks to some friends who help us to do some simulation, the reason is that we conclude that there is, the graphene helps to avoid the formation of a water meniscus, or at least reduce it at the D-sample junction, because the graphene is a hydrophobic material. This conclusion was extracted by measuring IV curves with both tips. And as you can see here in panel A, with the normal tip measuring on silicon, we observe that the shape of the forward IV curve, which is the blue, shows a sudden breakdown, a sudden current increase, which looks like a breakdown of a dielectric, and there is a shift towards lower potentials in the backward curve, which is the red. So basically this means there was a dielectric there and we broke it. Even if it was only silicon, which is not insulating, it behaves as an insulator. When we perform the same study with graphene-coated tips, we observe overlap of the forward and backward curves, which moreover show a current trend that is similar to what is expected in a metal-silicon junction. So we performed some simulations and we concluded that this difference between the forward and the backward IV curve are related to the presence of a water meniscus of 1 nanometer between the tip and the sample. And when there is electrical field applied, this water meniscus can be broken, and then the backward IV curve somehow overlap with the Schottky conduction that is expected. So this was one nice application that we did in my lab for combining 2D materials and conductive atomic force microscopy. And for this invention, my student patented this work. She published it in nanoscale. She also patented it. And one institution in Beijing gave us some funding, nearly $1 million, to try to produce these tips and commercialize them. And in the last section of this presentation, actually here there is an errata, this should be section 7. I wanted to show some of our most recent work in this, using the conductive AFM to analyze different kinds of nanomaterial. In this case, ultra-thin dielectrics. Dielectrics are super important. Most of you probably know it, but the main reason is that and they play a very important role in field effect transistors, which have allowed us to produce unprecedented progress, technological progress in human history. The miniaturization of this device brings us many opportunities for high density electronics. However, the problem is that it fails at the dielectric, and therefore studying new materials that could be implemented as dielectric in future transistors is very important. These future transistors may be made using two-dimensional materials. So finding the dielectric compatible with 2D materials like graphene or molybdenum disulfide is something extraordinarily important right now. So in this slide, I summarized some of the works on 2D materials-based field effect transistors in the literature, some of the most impactful works, and you can see something interesting. Most of them use hafnium oxide, high-K dielectrics, aluminum oxide, or silicon oxide for these studies. However, this is an important problem because the interaction between traditional three-dimensional dielectrics and the 2D material is very problematic because the 2D material doesn't have dangling bonds, and therefore we cannot form a conformal coating. So basically what you get if you try to deposit, for example, hafnium oxide on molybdenum disulfide is some dielectric islands that are confined at the defects in the 2D material. So in order to avoid this problem, in our group, we think the first strategy that we thought is let's try to go over fully two-dimensional structures. That means using a two-dimensional dielectric. And among the family of two-dimensional materials, the one that has better dielectric properties, the one that has higher band gap is hexagonal boron nitride. So this is the material that we started to analyze. And the study that I'm gonna show right now is done with one advanced conductive AFM. Is a very new tool that we have acquired in our lab. Is the NX-HIVAC from Park Systems. This AFM is unique. This conductive AFM is unique because it allows you to perform 4 different tasks simultaneously, which is measure in a vacuum chamber, measure with a logarithmic amplifier, measure at high temperatures, connect a semiconductor parameter analyzer, and also we can measure the current in tapping mode, which is very important to avoid lateral friction. So this is the only AFM in the world that can do this. We have used this to analyze multi-layer hexagonal boron nitride. This material is polycrystalline and it has been grown on polycrystalline copper. So in figure A and B, you can see the topographic and the current maps obtained on polycrystalline boron nitride grown on polycrystalline copper foil. And you can see something interesting. There are 3 regions that show defects. One is the grain boundaries of the copper foil. The other one is the grain boundaries of the boron nitride. But if you zoom in inside these boron nitride grains, what you observe is that this in panel C. The scale bar in panels A and B is 20 micrometer, and the scale bar in panel C should be 100 nanometer. What you can observe here is that there are some regions in this multi-layer hexagonal boron nitride that are more conductive than others. So what we did is to analyze the electrical properties of this material by applying constant voltage stresses and measuring the current over time. And you can see very clearly in panels E, D, E, F, and G that some locations don't show any current for the voltage applied and just show electrical noise, like in panel E, which was measured in one location that was completely white in panel C. That means there was no current. So when the boron nitride doesn't have any defect, it shows very low current. And in panel F and G are collected in points. In one of these points black points shown in panel C. And you can see clearly that they show fluctuations between two levels. This is what we also call a random telegraph noise signal, and it can be analyzed. So this is one of the beauties of the conductive AFM. You can analyze the behavior of every single defect and make statistical analysis of the conductance and the current levels of shown by each single defect. Later, this allows us to predict that because this dielectric shows random telegraph noise, which indicates abundant charge trapping and detrapping, we could find that the dielectric breakdown process is not so severe and it can be recovered. So basically, we use this material to fabricate some electronic, memristors that can fluctuate between the high resistive state and the low resistive state. And this can be used to store digital information. We published this work in Advanced Functional Materials, and after that, we also noticed that if you apply some specific electrical stresses, you can even induce some potentiation and depression in your material. So basically, you can use this dielectric as electronic synapse. This work was published in Nature Electronics in 2018. I'm sorry here, this reference is wrong. This is a Nature Electronics paper in 2018. I will show you the reference later. So we found that the boron nitride was very useful to be used as resistive switching layer. However, it cannot be used right now as dielectric, as gate dielectric in field effect transistor due to the presence of defects, as you can see in these TM images and in the current maps that I was showing before. So because the methods that we are using right now to produce this material at the wafer scale, which is chemical vapor deposition, are still producing samples with high density of defects, we started to explore also other potential candidate materials as gate dielectrics in 2D materials-based field effect transistors. And the material that we studied in this slide is calcium difluoride. Here you can see cross-sectional TM images where you can see the bonding, and we compare this material with 3 other samples. One is silicon dioxide grown by thermal oxidation at the laboratories of Infineon Technologies, which means this is outstanding quality silicon oxide. Also one sample that is titanium oxide grown by atomic layer deposition, and also one sample that is mechanically exfoliated boron nitride. And what you can see, if you perform hundreds of IV curves at different locations of each sample, you can see that the calcium fluoride shows the lowest deviation of the IV curves, which indicates that it is the most homogeneous material of all of them. Here we are seeing that the boron nitride is also somehow homogeneous, but this boron nitride is fabricated by mechanical exfoliation. If you repeat the experiment in CVD grown boron nitride, you will see a much wider deviation. So the boron nitride in this case cannot be really considered as a dielectric for wafer scale integration because this method is not scalable. So comparing the calcium fluoride with silicon oxide and with titanium oxide, we observe outstanding results. And we also performed one additional experiment, which was to scan again, to repeat the IV curves at different locations, but in this case, using the logarithmic preamplifier provided by this AFM. And what we could observe clearly is that the calcium fluoride shows sudden breakdown, dielectric breakdown, for all the positions analyzed. And if we calculate the dielectric strength, because we have the electrical field applied and also we have the bias applied, and we also know the thickness. We can calculate the dielectric strength. Till here is the end of my presentation. Here in this slide, I want to share with you all the publications related. The most recent works are also underlined, which are some of the most impactful. So I think if you want more information, you can check these papers and also the book that I mentioned at the beginning, which is titled Conductive Atomic Force Microscope. So until here is my presentation. Thank you very much for your attention. If you have any questions, please transfer them to us. I believe that Vinicius can also provide more details. Thank you very much.
Thank you very much for the splendid lecture, Mario. So now we are starting the Q&A section. The viewers have been sending their questions during the talk. So I'll start with the first one of them. This is from Sergio Bumpy. He asks, what is the sharpness or tip radius of a typical nanotip you use in AFM? And what's the typical mechanical sweep velocity in microns per second?
I see. The radius of the tip, you can see here. Oops, sorry. Let me see. Okay, here you can see my slide, right?
Yes.
So the radius of the tip of the AFM, it can be different for different types of tips. It can go from, let's say, 2 nanometers is the smallest, up to 200 nanometers, depending. Depending on the coating that you use, you will increase the radius, but at the same time, if you use thicker coatings, you will increase the stability of the coating. So it's a kind of trade-off. It depends on which material you use. You will get one more stability, but less resolution, or the opposite. The scanning speed that we use normally is measured in micrometer per second, but also can be measured in hertz, which is the number of lines per second. So basically, normally what we use is around 1 micrometer per second is something fine, but it can be also higher if you increase the size of your scan.
Okay, Mario, I'll ask you to turn off your camera. I'm not sure if it's on.
Yeah, sorry, go ahead.
Okay, we have also another question from Sandro Ferreira. He said, thanks for this impressive presentation. And then he asks, which are the simulating tools you are typically using, and how well they compare with the real measurements?
Sorry,
he's probably talking. What?
Sorry, can you repeat the question, please?
Okay, he asks, which are the simulation tools you are typically using when you compare your data with simulation results, probably TCAD results, and how well do they compare with real measurements?
That is a very good question. That is a very, very good question. So when we measure, one of the main theoretical studies that we do is when we measure the IV curves at different locations of the material, we can do also fittings. We can fit these IV curves, which are measuring the leakage current, to different conduction mechanisms, like, for example, direct tunneling, Follen-Nordheim tunneling, trap-assisted tunneling, Poole-Frenkel emission. So there are different types, and this calculation, this fitting, can help us to understand which is the way in which the electrons are flowing across this dielectric. That is the main study that we do. However, I have to say that right now we are doing one study that consists on trying to calculate the band gap, the position of the energy bands, and the formation energy for vacancies in locations of the boron nitride that are perfect layer or that contain some defects. And this is also, this can be done by DFT or by ab initio methods. So I think this is also something that could be done. There is a space for people working on simulation to let's say to complement conductive AFM studies. It is a very good match.
Okay. We have a question here on Zoom. Jerry says, nice presentation. One question about the growth method of CAF2.
Yeah. So this material is grown by molecular beam epitaxy. Actually, that is something also nice. There is a big difference comparing the boron nitride with the calcium fluoride, which is the calcium fluoride can be grown at 250 degrees, while the boron nitride is normally grown above 700 degrees. So the thermal budget is totally different, and that makes the calcium fluoride, it is realistic to think that calcium fluoride could be grown on a wafer. So on a wafer with something patterned on the wafer, so it will not destroy what it is in the wafer. I have to say that we have studied calcium fluoride because calcium fluoride grown by molecular beam epitaxy can form a quasi-van der Waals structure. It means the surface of the calcium fluoride is terminated with fluorine atoms and they don't have dangling bonds. So the interface between molybdenum disulfide, for example, and calcium fluoride can be very clean. And for this reason, we are considering this material for 2D electronics. And this is the main point. The calcium fluoride is grown by molecular beam epitaxy.
Okay, there's another one here, Zoom from David Perez de Lara. He said, thanks a lot for the nice presentation, Mario. I have a couple of questions. Do you have data of the conduction filament size for different materials? And the second question is, what's the minimum thickness of calcium fluoride and HB and to have a reliable dielectric?
Okay, so let me start by the second. For calcium fluoride, the material that we have analyzed in this study is 2.5 nanometer. And with 2.5 nanometer, only 2.5 nanometer, we observe an onset potential that is 6 volts, which is similar to the onset potential of silicon oxide when grown by thermal oxidation, and the silicon oxide is, as you can see here, 4.7 nanometers. So it is a really, really good dielectric. With only 2.5 nanometer, you can already have something that is quite insulating. And about the first question, the size of the conductive filament, there is something I should highlight, which is, as you can see here, when we create the conductive filament at the beginning, we need to apply a current limitation. If we don't apply a current limitation, it doesn't matter you make the stress at the probe station or you make the stress with the conductive filament. You need to apply a current limitation. Otherwise, the dielectric breakdown phenomenon is a thermal phenomenon that is self-accelerated. So if you don't apply a current limitation, you're going to make a permanent breakdown. So if you want to make a filament that is switchable, you need to apply a current limitation to limit its size. So basically, the size of the conductive filament is related to the current limitation that you apply, not so much to the material. If you apply in aluminum oxide, hafnium oxide, silicon oxide stresses, you can make the filament in silicon oxide wider than in aluminum oxide just by changing the current limitation in those stresses. So the higher the current limitation, the wider the filament. At the same time, I have to say that there are some materials, like for example, mechanically exfoliated boron nitride, that they show a little bit different breakdown phenomenon. The mechanically exfoliated boron nitride, when you apply the dielectric breakdown, normally produces one crater, one explosion. And this material there is physical removal of material. You make a hole. So that is a destructive breakdown event. It was published in ACS Nano in 2015 by Professor Keisuke Nagashio from Japan. And this is a kind of a little bit different mechanism because the penetration of defects in the boron nitride only happens at very high energies, and then it's very difficult to control even if you apply current limitation.
Okay, thanks. There's another question from YouTube. Juan Pablo asks, what a great talk. About the graphene-coated tip, how do you control the height, tip radius, and the tip full cone angle? Muchas gracias.
Yes, that is a very excellent question. And I have to say that here in the image that you can see in the right, you can see very well that the graphene is coating the apex of the tip. I have to say something. We are putting a tip that it's a chip. The chip, you can see the chip of the AFM tip here. Okay, this is cantilever containing the tip, and this cantilever is attached to a large chip. This chip you can take with the tweezers. Okay, so when you have the solution containing the graphene, you immerse the tip with the tweezers, you take it out. What you get, if you are lucky, well, let me correct, not if you are lucky. What you get is this, what you see in this image. And let me say not why you are lucky, because the point is that the graphene doesn't attach everywhere, but the sharp shape of the tip increases the van der Waals attraction. So van der Waals attractions are much higher in sharp geometries, and for this reason we observe that the probability to get graphene attached to the sharp apex of the tips is much higher than in any other location. And most of the tips that we apply, I'm talking about above 90%, they have graphene on the apex. However, I have to say that there is one critical parameter that Dr. Fei Hui tuned very, very well, which is the density of graphene in the solution. If you put too little amount of graphene in the solution, then you will not get tips coated. And if you put too much, you will get a big amount of flakes on the apex that they will not make your tip suitable for AFM measurements. So what you are seeing here is the optimal coating.
Okay, thank you very much. I think that these are all of the questions the viewers asked. I here ask for the viewers in YouTube to subscribe to the channel so you can have notifications of future lectures like this one, as the ones organized by the solid state part of the chapter. Once again, the chapter, thank you a lot for the lecture. And we hope maybe to have you here in the future as a distinguished lecturer so that you can travel after this pandemic situation.
Thank you very much. Thank you very much for everybody who was watching the presentation. And if you want more information, you can check the related publications, or also if you are interested that we evaluate the local conductivity of one of your samples with Conductive AFM, please feel free to send me an email.
Okay. Thank you very much.
Bye.